Yeah, well, okay. I mean, these are giants of our field, whom I greatly admire. From a style point of view, I would say I'm not even going along the path of Newton. That's not who I am. In that sense, I'm a more empirical experimentalist who has learned that we are in an epoch where new technologies, if applied in a clever way in fields which otherwise have not made progress or which are hard, can lead to enormous progress. So this is where, if you like, Galileo is closer. But again, I would say these are giants. My God, this I would not see as something I want to even dare to be compared with. I think where I would say my motivation clearly came from is, as I said, I knew already from my studies with my father, and then certainly once I was in Berkeley, that the infrared band from the near optical all the way to the millimeter range was going to be extraordinarily interesting for a number of reasons. First of all, many of the phenomena which we are looking at in the universe happen at relatively low temperature, such that optical radiation just is not produced. Next, again, Townes' insight already in the 50s, believe it or not, that the universe is full of molecules whose radiation you can then use in both analyzing the content, the physics, and then also the motions of gas in regions where stars are forming, and etc. That was so important. And the astronomers wouldn't believe it, because this is a story from Townes. Townes gave a talk at an International Astronomical Union meeting in 1957. You might want to have a look at it. It's absolutely stunning, that talk, because it predicted the future of molecular line astronomy for the next 30 years. And all the astronomers, and he told me that, or some of the famous astronomers, would come to him in Berkeley and would say, "Oh, Charlie, this is nonsense. There is so much ultraviolet radiation out there because of the stellar radiation, etc., that molecules can't survive. You won't have molecules." And then a few years later, Townes and others came to this revolution. So this is there are tools there in this wave band. There is the fact that cold gas, cold dust clouds radiate there. There's, of course, the redshift of distant galaxies shifting things into the band. So it's a treasure area to be discovered. I was fairly certain that would happen, and it did happen. And so this is where already in Berkeley, but then certainly over here, by developing certain new areas of research, we were able to break into new questions. One of the questions then was the issue of the black holes and gravitation, and whether these weird predictions of Einstein's theory were actually realized. Now, I was not aware of this intense discussion, I must say, from a deep mathematical point of view, which I now appreciate from Roger Penrose, since I'm listening to some of his talks. I'm not sure I understand all the arguments, but certainly for me, the Schwarzschild metric was good enough in many ways. I mean, to question, this discussion in the early 60s, whether a highly symmetrized solution might be too symmetric to be realized in nature, that I had not appreciated. But as we all know, of course, there weren't any candidates until the 60s where one might go after. Then came the X-ray binaries, Riccardo Giacconi and all of that, and then came the quasars. And Towns's reaction was due to the famous paper by Lyndon Bell and Rees. I mean, the quasars were so far away, billions of light years, so you couldn't obviously make any reasonable measurements of the space-time, the curvature of the space-time, which was needed, and see whether there were these compact masses. But if you would have such compact black holes in the Milky Way or nearby, then you could. That at least there was sort of the qualitative picture. But then how would you do that, given that in the Milky Way, between us and the Milky Way center, there's 10 to the 12 of extinction. So no optical radiation, no optical photon really makes it to us. And that's where Towns comes in with his infrared equipment and the first work. So that's, as I describe it in my Nobel lectures, these phases where, initially we started with gas clouds and looking at their Doppler motions, finding indeed that there was quite a bit of evidence for a central mass, all proud, writing a Nature paper in '85, here's a black hole, and everyone else saying, don't believe a word what you're saying, because gas clouds, especially if they are ionized gas, don't have to follow gravity and can be pushed around by all kinds of other stuff, magnetic fields, winds, and so forth. So this was very clear that we needed to make a big jump and look at the stars and get at their motion, which in the 1980s, with Towns's the equipment we had in Berkeley was not possible, and you needed new detectors, and you needed to go to bigger telescopes. All of that became sort of a possibility once I could take these risks here in Garching to open up new areas of development. But then it took us, I would say, 10 years before we were, in that sense, competitive, and actually came. So I guess the real, if you like, the real thing was the fact that the quasars had, and then more broadly, the active galactic nuclei had put this paradigm on the table. Every galaxy has a big black hole in its center. And now let's check it out and be physicists about it and not just astronomers. I mean, the astronomers, they believed it easily in '85, right? Relativistic jets, gamma rays, X-rays. Hey, how would you do that without accretion onto a relativistic object? But to go the route of measuring the space-time through test particles is really the route which has been the successful one, number one, in our case. Number two, if you like, with the gravitational waves. I mean, it's the same in green. And then also the event horizon approach through photons. So that's where things have been heading recently. Of course, it's jarring almost that it took 100 years for this to occur. And I must say, many people have asked me this, were there phases when we were ready to give up? Well, no. I mean, we had setbacks. Of course we did. My God, did we have setbacks? Everyone has who builds instruments or does theory, whatever. But the Galactic Center, as I say, always delivered. And often it was a lecture in humbleness of theory in astrophysics. We are all, in many ways, you mentioned Newton and then, of course, Einstein. So the picture we physicists have we not, is that it's these giants, these geniuses who, prophet-like invent things, and then the experimentalists go and check. But if it comes to astrophysics, it's very rarely that way. Quite often, the complexity of the system is such that, it's true, of course, gravity dominates, but then there are other things which also happen, and the timescales are dictated by other things than you think, and then the many objects you have make complex structures which you never would have thought about, and in the end, to understand all of this is driven by the observation rather than by the basic reductionist theory. Yeah, I very much agree with you. And it, of course, gives you also a bit of a pause, because it shows that people have these absolutely obvious, you would say, if you understand Newton, but also stunning ideas, which go way beyond anything which would seem reasonable, which turn out to be 300 years later right, but everyone forgot about it, right? That is also, I mean, it's quite stunning. People forgot about Mitchell, and I guess, let's see, who was it? Was it Eddington who dug him out? I mean, this is not that he sort of came out of his grave already with Einstein. I don't think Einstein knew about Mitchell. But after all, you can also say, you know, Einstein wasn't all that interested in the Schwarzschild solution, was he? I think it's different motivations. I do know, having talked to Roy Kerr about this, that he said, well, look, after all, the Kerr metric paper and the quasar discovery paper of Martin Schmidt happened in the same year, 63. So I asked Roy, so how did you react to the discovery of the quasars? And he said, I didn't know about this. He said, we wouldn't talk to the astronomers. We were mathematicians, come on. And you see this in Roger Penrose, actually, also. I mean, he's delighted by generalizing the mathematics, but whether this thing actually exists. There was one thing, however, which I have to tell you, which is very recent. So Roger and I were on, and there was a discussion going on. And since, of course, last year, so many people have written to me about wormholes, and I'd never really know what to say, other than, well, okay, there are vacuum solutions, and you put dust in there, and the solution breaks down, and so forth. And I said, so Roger, what would you say about wormholes? Oh, rubbish. That was great. I'll use that from now on. I say, oh, Roger Penrose said rubbish. Because I have to ask Kip whether he would agree with that again. No, it's. I mean, obviously, that if you know whether I've told you this or whether you know this, if you type into ADS or one of these servers various words like gravity, black holes, and you plot that as a function of time, he is stunningly close to an exponential, still now. And I find this absolutely fantastic. And of course, now with the discussion of whether dark matter might not be black holes after all, and the whole issue, of course, of the multiverses and the Big Bang and all of this, it's just incredible how what we thought was a fairly straightforward classical theory, well understood mathematically at least, and now even calculable in extreme situations for the purposes of numerical relativity in gravitational waves, that this theory excites so much and is, in the end, of course, information paradox, lack of quantum theory, etc., so modern and so interesting. Right? No, I think it's absolutely true. I mean, and it's such a fundamental thing. And in the way I, at least in talks, try to explain all of this is very much in two ways. People come into this, oh, black holes, ooh, this is so complicated and so forth. And I say, actually, no, it's very simple in the way we've discussed historically. Namely, number one, you only need to know the Michelson-Morley experiment. Okay, that's a simple empirical fact. Okay, nothing goes faster than speed of light, and speed of light is a quantity in vacuum which you can measure, and that's it. Number two, that if you take the Newtonian approach, then you can immediately see, since photons see gravity and curvature of time, space-time as well, that you can construct a case of an object where gravity is strong enough that the photons can't escape. And there you go. There's your black hole. And of course, then comes the stupid singularity, which can't be right. And that's the fascination. For us, we are not allowed to go there. So how do we do this? Yeah, how do we physicists do this? This is a real challenge for the future. Likewise, the information paradox. Can we measure the Hawking radiation? Maybe after all. Maybe there is a way to see deviations from a Planck spectrum, which has signs of that the information content and so. But I mean, I also know that this is going to take long enough that maybe another 100 years is easy to go by before we see that. But as I think you had heard me say in talk, that I do believe that if LISA can be launched and will be launched, that this is going to be a great step forward, because then we can at least measure the chronometric to high enough precision and test out the no-hair theorem. What you're seeing is the presence. We have a star which is actually fainter than S2, going through Peri, closer to the black hole than S2 years ago. This star is, it's called S29. It has an ellipticity of 0.97. That's pretty good damn aiming. That's, you have to really, shoot pretty straight at the black hole. And it is going to dive. The Peri will be in 3 days. And in 3 days, it'll move at 9,000 kilometers per second. And it'll come as close as 96 astronomical units. So that's deeper into the potential than S2. And it's currently down below. You see an image, in fact, of last night. It's now closer than S2 ever was. It's 11 milliarc seconds away from the black hole. We didn't know about this. This is absolutely astounding. And here we are having fun, trying to do all kinds of measurements. And here the star comes in. We knew, of course, we knew about the star. It's not that we didn't, but we didn't have accurate enough data to know it was exactly on such an orbit. And this only became clear over the last few months. And just imagine 3 years. And this thing goes, as I said, to 90 astronomical units, where S2 went to 120. So I'm beginning to compare this now to a situation. And this star has a period of 90 years. That's because it's so elliptical, extremely elliptical, while S2 was 16 years. But obviously, what we are beginning to recognize also, there are other stars. This thing is full, and boy, what is the probability that they collide? I mean, this is like, I compare this to motorcyclists in the Alps here, where they whiz around the turns, not looking, whether there's a car coming. And, there's these stars too, within 3 years, essentially on the same trajectory. And of course, as you know, once these things come close to each other, three-body is going to be so fierce that it's going to throw one of the guys out. So we are, as it happens, we are right within 2 days of another star pairing. So the 1990s was the period where I mentioned we were busy developing the kind of instrumentation which was needed. We knew we wanted to look at the motions of stars, so we needed to have imaging cameras in the infrared, mind you, because optical doesn't work. And we had to beat the Earth's atmosphere because the seeing, due to the motions of the Earth's atmosphere, refraction, is so bad that you can't see anything if you don't remove that. So initially, we did that by making very fast photos, if you like. It's called the speckle technique. And for that, we needed a good camera. And that camera was available in the US in the military part. But then the Space Telescope was equipped with it, would get equipped with it too. So you managed to get one of these cameras out here. And then we asked ESO to let us use their test telescope for the VLT, so-called NTT. It's a 3.5 meter telescope. That's how we started. Then we developed also imaging field spectroscopy. That was a second thing. So we were building up technologies which then would be needed now to do this experiment. And we wrote to the director of ESO, if you let us use your telescope, we think we can measure the motions of stars around the galactic center. Sort of in a period of 5 to 10 years, we'll be able to see something moving. And indeed we did. And then the Keck group, of course, started a little later, but they had already the Keck telescope. Then we moved to the VLT, and then it became a very close alliance because from now on, we really focused on the VLT, developed ever more important instrumentation. And once we had seen the first peri of S2 in 2002, of course, we knew the star is going to come back in 16 years. And when it does, that's when we need to be able to make measurements which allow us to test GR. So this is when the experiment moved from, showing that there was a massive object there to can we test general relativity in a quantitative physics fashion, so to a laboratory approach. And for that, we needed to have higher resolution, and that's where the idea became clear that we wanted to use all 4 telescopes, which was crazy. I mean, it was sheer crazy. To build gravity was impossible. Towns tried it. He did do interferometry, but he failed by a million in sensitivity. Okay, so that gives you a bit of a feeling of how far we had to go, and we did manage. And now we're in this situation where Paranal is the machine, very clearly the machine to do this kind of stuff, because not only are we very precise, we also have the resolution to see several things, including the black hole itself. I mean, that's obvious. So that really has been a very, very important collaboration for us. And I would hope for ESO as well. Now, ESO, of course, has to serve a large community. So in that sense, it's not always possible for them to give us the opportunities we want. In fact, once Chile had its first big wave, they had to cut down the observatory completely for 9 months, and we lost basically all of last year, and just barely opened up for March when we made our first measurement. That's when we saw that star coming in, and then they had to close it again because the COVID numbers would go so high. And there's only, believe it or not, only 2 ventilators in Antofagasta. It's incredible. 2 ventilators for several million people. Absolutely incredible, yeah. And I mean, honestly, I have to say, if I would have been Director General of ESO, I would have tried to see whether one couldn't fly, pay from ESO money for a few ventilators and fly it down to, because I mean, we poor people down there, and second, this would have been some sign of help from a European organization to the Chileans. Anyhow, I mean, we are now just opened up again, and here we are making this measure. It's just an absolutely fantastic experience. And we are going on, we are improving things further. And then comes the ELT. I'm afraid will be beyond my retirement, but still it's absolutely wonderful story. It would have been even better if Brazil would have joined. That part of the story you tell me about, I don't understand it. I don't understand it. It's okay. I mean, ESO has made up for it to some extent by courting the Australians, but that's actually not enough. And it would have been so obvious an enrichment of both communities. I don't understand it. Straightforward, but then also a tricky issue. It's straightforward because the way it started, as I described it, was I was coming, if you like, from a well-known research group of Charlie Towns who had been doing this already for a decade, and was then going the next step. So that was sort of, if you like, my way, and the technology I mentioned. And the facility ESO was the obvious one. So that's very clear. The other side is also clear, because the tradition there came through Gary Neugebauer and Eric Becklin at Caltech. Eric developed in the early days, just like Charlie Towns, infrared astronomy in slightly different ways. He came from the shorter wavelength, and Eric Becklin, his student, became a very powerful figure. And I've worked with Eric Becklin quite a bit, so I know him well. I like him. And Eric, when he moved from Hawaii to UCLA, immediately started thinking about the stars also. Now, he thought more about the spectra of the stars than proper motions, but anyhow, he knew what he wanted to do. And now comes Andrea, and Andrea came from Gary Neugebauer's group, okay, did her PhD, and after the PhD, immediately went to UCLA, and there you go. I mean, it's very obvious that to them, opening up a research effort experimentally in the Galactic Center with the Keck telescope is a straightforward thing to do, and I think absolutely correct. Now, it is true that at that time, we were already, if you like, a little bit ahead, because we had started earlier. Andrea and Eric needed to get external money, which we didn't. They started in 95 to do the proper motions. We had started in 91, but then we had the smaller telescope. But the thing which is essential here is the scientific principle. Okay, so here we go and come out with a paper, or 2 or 3 papers, in fact, in 96 and 97, where we basically laid out our case based on the first 40 motions statistically, that there's a mass, which is the same mass as we had seen with the gas clouds, but now on a smaller scale. And so the evidence was getting stronger. Not that it was not there before, it's just gotten much stronger. Why should you believe us? They're very difficult measurements to make, and people were skeptical. Even Towns was skeptical. I mean, he knew, of course, very early on what we had. So I showed him already in 95 our first indications of the proper motions, and he said, "Oh, that looks very good, Reinhard. But before you publish, make sure, that it's right." So in that sense, what better thing can happen that we publish, and then a little later they publish, and we come up with the same result. Everyone believed it. See, so that's the beauty of it. Everyone believed it. So by end 90s, when we were sort of done with this phase where we measured some proper motions of fast-moving stars, and the case got pretty good, I think we were very happy with each other. We liked each other a lot and had a lot of exchange and so forth. It got more troublesome in the sense because the next phase, again, was one with lots of technology. Now adaptive optics came in. Now we moved to the 8-meter class telescopes. And there it became really a sort of a side-by-side competition where everyone would look at the other side. I would say it was okay, but from time to time, one would make maybe a remark too many, and the other side would get a little, angry and so forth. But that was okay. It's all within limits, I would say. Nothing really wrong. There was more, Luis, but I don't want to get into this, okay? Because I made an honest German remark on this in the Spiegel, and it got me into a lot of trouble. And I understand why, but that's the German way. We say what it is. But I don't want to. I don't need to relive this. And from my perspective, and Andrea will formulate it the same way, is the beauty was because both groups got more or less the same way, and then this got ever better over time. That is what made the believability of the case so strong, and even the physics community would accept it then. See, the astronomers, easy, but the physics community was much harder because for them there was, and I'm sure you appreciate that, quite a fraction of the physicists said, astronomy, this is this, order of magnitude stuff, where you never really know what's up. But the galactic center was different in that sense. That came and helped us. And then the fact that both groups, again, took great advantage of the pari number 2 in 2018, measured the gravitational redshift and so forth. Now, what is open right now is that Andrea has not yet seen the Schwarzschild precession. And that is the difference between one single 10-meter telescope and an interferometer. We just, in that sense, we could measure better, but I hope she will get it anyhow when the star goes through Apo. And if she can correct for the drifts in the reference frame, well, then she should be able to get that. Whether we get the next step, which is a spin, that will be hard for both of us. But anyhow, I'm in that sense, this is good. It does have slight bite tastes, which are not so good, which have again to do with this Europe versus America issue. Americans do sometimes, I'm sure you appreciate that they do sometimes, they're very nice people and I like them a lot, but sometimes they are a little on the arrogant side because they have won for a century, right? They have won all the wars they got into. They won. And now it's sort of, and every president, even Biden, even Obama, when they made the State of the Union speech, would make these statements like, the unique excellence of the American people, or the fact that we are leaders by. I mean, this is part of America, to want to lead and to be leaders. And if somebody else challenges you in that, Americans don't like it so much. And so that's the part which I would say, we all need to be aware of, and as scientists, be sure that we don't go from competition to, this kind of stuff. But it's not, in this case, we're okay, I think. Okay, number one is I was 99.9% sure that we would not get the prize because Andrea and I had gotten the 2012 Crawford Prize. And I know that we got the Crawford Prize. Let me say, I suspect strongly that we got the Crawford Prize because we lost the competition with dark energy. I do know we were considered for the prize back then in 2011. And dark energy was, and I understand that, the more exciting discovery for the physics committee, and they went for that. And so then we got a Crawford Prize, and that was just it. And then I very much appreciate that, and I think that's great. In that sense, I was not sitting there since 2012, and in every October I would get the jitters. No, absolutely not. I was very certain that was it. Whether there might be more, well, another chance, maybe. the interferometry I thought was profitable enough that if we could get these GR terms, I thought maybe we would, we might have a small chance. So it came me very, very surprised, very, very surprised. I say of all the Nobel laureates of this 2020 epoch, in a way, I was, in retrospect, one of or maybe the most lucky and privileged one, because most everyone in the US had their prize transfer in their gardens or at home, because the lockdowns came. As you may recall, in December, the lockdowns happened very rapidly in late December, and so, or early December, and so that meant that Andrea and others all got their prize given by a Swedish ambassador or somebody giving it to them at home. Not so here, because the Bavarian government, our governor here, allowed us and was present at his own big Staatskanzlei, as it's called. It's a big building, beautiful hall, to use that. And that allowed us to have a real ceremony. Again, there was a Swedish ambassador who came, but I actually was able to have several guests, including from my own group working on this, some of my family, as well as the president of the Max Planck Society, etc. So it was much more of a nice ceremony than getting the plaque between the garden door and the garage. I mean, so in that sense. Now, of course, I knew from other laureates that once you get the prize, two things happen. Immediately, one of my colleagues, the president of the European Research Council, ERC, wrote to me and said, "Reinhard, you know, right, that now comes the hardest period of your life." And others would say, "You know that you won't do anything but traveling." So let's start with the traveling. The traveling did not happen, and that in a way was okay. I would say, to the extent you feel that I've done a reasonable job in giving Zoom talks, I would say that I'm reasonably happy. There are people who don't like the Zoom talks at all. I don't mind so much. So it's possible. Of course, you don't get the human interaction, that's clear, but that was okay. The other side is something you need to learn, and there I guess I was not perfect, which is now all of a sudden you're someone everyone asks for everything. Now you're supposed to have opinions about everything. And you heard me now a little bit, at least a few hours. I'm a pretty straightforward person. I'm a straight shooter. I'm a German. I say what I think. That's appreciated in Germany, but not necessarily elsewhere. So, yeah, I did make some comments about American politics. This was right before the election, or right past the election, where Trump was fighting against it. It was not at all popular. Was in the U.S. As soon as my colleagues heard what I had said. Although they hated Trump, but they didn't want to hear from a German that Trump was, So in that sense, I had to learn. And I have to say, I have continued to have a number of the format we're having here in Germany and German speaking, because I guess the audience does like hear my straightforward style, and I just have to watch it so to go overburden and make mistakes. That is a big mistake you can make, and some Nobel laureates have done that, and that's not good. There might be, it's a great honor to start with that, but there might be the fear, of course, that on the theoretical side, that there definitely were and are others one should have also looked at. One of them is obviously Stephen Hawking, but he passed away. Another one is Roy Kerr. And Roy also got the Crawford Prize, by the way. Yeah, so he was, so to speak, the Crawford Prize after me. And okay, you probably know better how to judge, but I would say, for me at least, Kerr, for practical reasons, was what I learned first before I learned something about Roger Penrose, because I'm not a mathematical physicist. For me, the Kerr solution is the practical need be, okay? So how you have to couch your measurements, so to speak, that's what you have to understand. But in that sense, okay, the committee had to pick. You could, of course, ask, what about other experimentalists? And indeed, I would say the most common comment I get there is that a number of people not in the innermost circle were very surprised that the event horizon result on M87 did not get recognized. I'm not surprised, because it was not a physics experiment quite yet. It could be a physics experiment, and it hopefully will be a physics experiment if they can do the galactic center. There, the problem is just variability. They cannot make good enough images to see the photon ring inside a star, because the source is too variable, which is what we see in the infrared. And therefore we see this going on as motion, but for the imaging in the radio, that is detrimental. But many people are surprised that they did not get recognized. But there you are. I mean, if you count the number of people who you would think have had very important influence on this sort of overall is fairly large. Okay, surely it's good that the gravitational wave community already got recognized, but in total, I mean, there is certainly a handful of individuals you would think has to do with this overarching big issue, and there's more to come. Obviously, there is. We talked about that. No hair theorem proven, so all of this shows how important the issue really is, and what needs to be done there. But anyhow, I mean, I have the greatest respect for Roger, and I'm afraid the mathematics he's doing is beyond me sometimes. It's clear that if you look at this particular issue from an experimental point of view, is that it took so long just because it's so difficult and the effects are so small. I mean, this is mind-boggling what you have to do to detect the gravitational waves of an in-spiral. It's perhaps not as mind-boggling, but it's still pretty mind-boggling what we need to do to make the detections we do. So it's very difficult experimental work, which doesn't come on overnight, and you need to wait until certain technologies can be done and can be developed, and that's been possible over the last years. Now, the next steps, at least for us, are obvious. We are in the process right now of improving the interferometer by what hopefully is another factor of 100. And that should give us, absolutely fantastic opportunities, not only in the galactic center, I should say, but also actually looking at quasars directly, which we are doing. We can now measure the masses of quasars through measuring the motions of the broadline regions. We also look at exoplanets. So, I mean, this technology has impact on other areas of research. Then the next big step is the still bigger telescopes, the 30 to 40 meter class telescopes, which will come in hopefully between 5 to 8 years from now. They haven't come in as fast as we originally hoped for a number of reasons, but they will come, and no doubt, and they will increase, of course, the sensitivity. And so then spectroscopy will become again a possibility at a level of accuracy which is going to be fantastic. We are waiting for pulsars. Should there be a pulsar in the central region, I would say that would sink us all, because the pulsar the timing of a pulsar can be done so much more precisely. Then you could do what I've been discussing, including these are all within a few years. But the surprising thing is no pulsars. Well, there's one magnetar, but a magnetar is not suitable as a clock. It glitches because the magnetic energy dominant is far. And so it's not suitable. And the radio astronomers are looking hard, have been looking hard for 30, 40 years now, and have not seen otherwise a pulsar where there should be, by any rights and means, hundreds of pulsars. So that's very surprising. It tells us something about this complexity issue, and that perhaps a formation of normal radio pulsars in an environment like this is cut off in the evolution of the stars. But of course, for the question of testing the black hole paradigm, it's not so great. Then there's other things which we want to do, of course. We want to look for other objects. I mean, it's astrophysically, of course, these objects naturally are not by themselves. Many people expect intermediate mass black holes to be there, and they would be very important for gravitational waves too. So that's something which, of course, we are looking at. And in fact, by measuring these precessions of the stars, that's a wonderful way of testing for that. And maybe one day we will see a star moving along and all of a sudden do this. Okay, just imagine. The chances are not zero. I mean, they are supposedly finite, probably finite enough that over a long period maybe you could see this. So there's great things one can expect. But now comes a but. The experiments we're doing now are at the level of, once the telescope is there, at the level of several tens of millions of dollars, euros, etc. So that can be done in collaboration of several institutes in Europe or in the US by a donor plus NSF and so forth. Can be done in international organizations, etc. But then the ELTs are $1.5 to $2 billion. And that's where the air gets very thin, because once you have a slip of something which costs all of a sudden 400 million more, yeah? So this is where I worry that we in astrophysics will, follow our particle physics colleagues quickly into a domain of size and cost, where, we cannot just go ahead very quickly in a research group or in a group of research groups like we've done. And that's the fun of it. That's working with students, working with young people and having them have the fun. I mean, yesterday we had a goodbye party for one of our postdocs who happened to have been doing this here in the group, and he was so grateful. He said, wow, I never would have expected to be part of this, okay? And I was part of this, and this is a great experience. And once you are 4,000 people working on a particle machine, that's not so fun. So this is where I see limitations. And we will, of course, also see to what extent our countries, after COVID and climate problems ahead of us, will be able to give us as much money for basic research as they have. And you mentioned in your own country that, or in the US, if you get the wrong leadership, all of a sudden, although things should be okay, they're not okay anymore because people go elsewhere. They want to do other things. So we must be vigilant and work hard. There, the communication with the outside world is indeed very important. That's where I have invested now, I hope, in a good way for all of us, because the interest of the community, of the everyday person in black holes is so large. It's just like that. What should I say? I mean, people find this fascinating. They say they don't understand it, but then you give them. I could give you an example. 1.5 years ago, an artist came, a woman artist came and said, "Professor Genzel, you're working on these black holes. I'd like to put these black holes into art. Could you help me?" So then I had a postdoc of mine visit her, and I visited also. And she, after a year and a half, she made a vernissage just this spring. Beautiful work, absolutely beautiful work. And it's clear she was fascinated by the subject. Okay, and this kind of fascination to communicate that to a larger audience is an important thing, because if the more people know about basic research and what it entails and how fascinating it is, especially also for young people, the more likely it is that the politicians will follow. I hope, but that's just a hope. Yeah, well, okay. I mean, these are personal remarks. Everyone will look at this differently. I mean, I never was driven by having to earn a lot of money. I did well enough, so it's okay. I've been extremely lucky in the career I've had, and believe it not, since now, almost 40 years or 37, 38 years, people pay me to play. This is fantastic. Okay. Now, it is true, you just mentioned that a little bit, that not everyone will be intense. I am intense. I'm impatient too. I want to get somewhere. I want to do things. And people say about me, "Oh man, Reinhard again is on Channel 5. And then people get angry. "You've been on Channel 5 the entire day." Meaning, I did, tunnel vision. And, but it's fantastic. Okay, there are these days which are not so good, and we all have them, but that would be true for any profession, I would have to say. And my luckiness doesn't end because somebody has said, "Okay, you're now 68 and you have to retire." So this is, again, very lucky that the MPG has allowed me to do a few years more. I hope I can fill them in a useful and practical way. One gets older, that's for sure, and then one doesn't get stronger. And so in that sense, one has to be a little careful not to overdo it. Towns, in the end, had one great goal. He wanted to become 100. And he wanted to become 100 sitting in the saddle. And he did sit in the saddle, that is, in his office, doing science until he was about 98. Then he had pneumonia, and you could see how he was getting significantly weaker. He missed 100 by 3 months. But he had a very fulfilled life. So maybe I won't turn 100, that's for sure. I don't have the genes for 100, but I think, as I said, dying in the saddle is sort of the kind of thing which is great. But for young people, they should do whatever they find exciting. I mean, not everyone is good at this. Others want to have more fun at the beach. They should do that too. And as long as different people can and are free to do their most favorite things, be excited about it.